Before I begin, I want to say a few words on behalf of one of our sponsors for this conference, which is Evolution. So, Evolution asked me to do this intro, and I agreed to do that because I believe in the team. I believe in what they're doing, and I know that these folks are first rate, great place to work. So, I'm going to go ahead and do this introduction tonight for all my friends at Evolution. So, first off, Evolution is a very large and successful company that's been growing even during these times in the pandemic. They have actually more than 450 different engineers scattered across Riga, Minsk, Tallinn, and Amsterdam. And I've personally visited all of their offices, and they're really located, actually, except the one in Tallinn, which I have not been to yet. And they're just beautiful places. And they're filled with the engineering team, just really kind, hardworking, smart people. And there's a whole bunch of reasons why you might want to consider Evolution for your next job, including the fact that they're an industry leader. They have amazing tech stack that's actually very forward thinking. So already they're using Cats Effect and Zio and Monix, and they're cutting edge both on the back end, but also the front end. They have a great culture. They actually do value high quality and integrity. I can speak to that personally. They're very knowledgeable. I think you may have gotten a taste of that when you saw their Monad quiz, which they asked earlier today. So if you haven't entered that challenge, please do so. You get to potentially win a $100 gift card to Amazon. It's a fun quiz. They also believe in code ownership. So really, you take ownership of the things that you create, and you're able to see that over its life cycle, see it grow up, see people use it, and that's very satisfying, especially if maybe you're used to more contracting positions, working in the position of a product company where you actually get to build the product and you get to see it and see it being used by users and maintain it and upgrade it over its entire life cycle is really very satisfying. They have service-oriented architecture. They contribute a lot to the global Scala community, including doing Scala boot camps, which I recently saw. I'm just amazed at how much effort they spend trying to teach people Scala, which is really great. I mean, obviously, as you can see, I think from this conference and all the sponsors here, there's tremendous demand for Scala developers. It's never been a better time to be a Scala developer than now. And Evolution is doing their part trying to help create the next generation of Scala engineers. They also do meetups and contribute to open source. In fact, if you want to see what some of their sort of cutting edge open source looks like, you're welcome to look on their repository. They have a really interesting project involving caching and Cats Effect that you should take a look at. And then they definitely invest into their employees. So every single year they have learning days multiple times a year, and actually I've been privileged to be able to participate in these learning days for the past 2 years, and that's where I met the engineering team and had a chance to hang out with them for lunches and dinners, and then during the workshops I really had a great time. So if you are considering working in one of these really wonderful locations, then I would give them a ring, talk to them. You can find them in the Evolution booth. Also, when I take Q&A after this talk, you can find me there. I think a lot of companies, they talk the functional Scala lingo. They promise Scala and functional programming, and you get in there and it's like, oh, well, we're a Spring Boot shop or untyped Akka actors that are 10 years old and no one wants to maintain. But that's not who this company is. Evolution is the real deal. So if you love functional programming, if you love writing Scala, and you're willing to work from one of these beautiful locations, then definitely give them a call, because I think you'd be very happy working for them. All right, we are ready to begin. So a year ago at Functional Scala 2019, I took to the stage to announce something that was very, very important to me. What did I announce? Well, you can see it there in the background. Ta-da, ta-da. I announced the formation of Zyverge, my company. I founded this company because I believe in the power of functional programming. I think actually statically typed functional programming has tremendous potential to revolutionize the way companies develop software. And these benefits, they can be seen, they can be felt. I'll give you a very pointed example later in my presentation today, but they are powerful benefits. And I think that truly statically typed functional programming in Scala even is a game changer. And we're in the early days of seeing all the implications of what that means. And what better way to advance that and also put my money where my mouth is, so to speak, by founding a company that's dedicated to using the power of functional programming to change the way companies do business. And so I founded Zyverge, or rather I announced its formation at Functional Scala 2019 because it was something that was very important to me. And then fast forward to today, I'm happy to say that we've had a great year. Even with the pandemic, we've been very lucky. I'm very grateful that we've had so much success in the marketplace. It's been an amazing year. And so I have no complaints. And if you know anything about me, you know I'm not the type of person who believes in zero-sum games. Maybe zero-sum games make sense if you're Oracle size, if you're in a very mature market. But if you're in an immature market, and I think that commercial functional programming in Scala is a very immature market, that is, our growth days are ahead of us, then actually I believe in win-win. I believe that when you work with other companies, then instead of fighting over, the 10 companies out there who need solutions in this space, you can together jointly create 10,000 companies who can benefit from the solutions that you're offering. And so thinking forward to our vision and just how much we want to accomplish here at Zyverge, it occurs to me that we can always do this alone, obviously, but it makes more sense to work together with other industry leaders to bring them on board and to together work towards a joint vision of massive success for statically typed commercial functional programming in Scala. And looking across the sort of ecosystem of companies out there, one company really stands out to me just for their significant contributions to the open source Zio ecosystem and for their investment in conferences like this and events like the Zio Hackathon and so forth. And that company is, may or may not surprise you, Scala C. Because I've been promoting them quite a lot during this conference. And that's because I believe that we have shared vision and alignment on what we want to see for the future of the Scala programming language. We want to see this thing succeed, and we want to see functional programming get its chance to shine in a way that it's not done so far. It has a little bit here and there, but our belief together is that its best days are ahead. And towards this end, it is my privilege and pleasure to announce that Scala C and Zyverge are entering into a strategic partnership. And this strategic partnership is going to represent for the community a tremendous commitment to shared investment in the open source ecosystem. So that's what you're going to see from Scala C and Zyverge is significant investment into the open source ecosystem. And not just investment into the ecosystem, but also investment into education and evangelism, because we want to equip developers out there to succeed using functional Scala. And that means education and evangelism. It means events. And then also, I think what you'll see from this partnership is extended training and development capacity from both companies as we're working together. And you're going to see a strategic shared roadmap that takes us out into the future, into a world where functional Scala is more successful than it ever has been before. So to say a few words on this partnership, I've invited the ICEO of Scala C, Matt Grant.
Hello, I'm Matt. Thank you, Sandra. Thank you, John, for inviting me. And hello, Functional Scala attendees. Scala for 7 years is at heart of Scala C. We believe in its correctness and expressiveness. From all libraries out there, we think that Zio is the best choice for the future. Also, taking into account that Scala 3 is around the corner, that's the best time for all of us. With a partnership with Zyverge, we would like to boost the Zio growth. We would like to help companies to accelerate their development in building the next future software using Scala and Zio. Let's do that together.
Awesome. Thank you so much, Matt. I look forward to working with you over the coming years. All right. We are all set for the next slide. If I can advance it. It doesn't want to advance. There we go. There we go. Okay. Here we are. This is your app on Scala 3. So this talk here tonight that I'm going to close this conference with is going to be a bit different than a lot of the other talks you've seen at the conference. This talk is not going to teach you something that's highly technical. It's going to be a big picture talk. It's going to be a talk that hopefully equips you with the big picture of what Scala 3 means to the functional programming and the Scala and even the JVM ecosystems. And my hope is that when you come out of this talk, you are equipped actually with tools that you can use to help make that next sale in your organization. We're all salespeople to one degree. And if you want to introduce Scala 3 into a Scala 2 code base, or you want to introduce Scala at all, or you want to get a Scala job or create a Scala opportunity inside a company that you work for, then you need tools. And tonight I'm going to give you some of those tools. So agenda. First, I'm going to try to talk you into the fact that programming is hard. Probably you don't need a lot of convincing because let's face it, programming is pretty hard. And then I'm going to argue that languages like Scala exist because of the compiler, because of the static type system that they provide. And that static type system, together with all the features that are built into the language, is here to help us make programming easier and more accessible. And that this help comes in the form of things that tangibly make a better difference to the company's bottom line. So this is not something that we emphasize. We don't choose new programming languages or choose to upgrade to Scala 3 from Scala 2 just because we want to play with the new shiny toy. No, these are real pains that these programming languages are solving, and they help us. They help us deliver better software in less time and maintain it more easily with fewer bugs than other solutions. And tonight, I hope I'm going to make a case for all of that in a way that's easy to digest and that you can package up and present to other stakeholders in organizations that you work with. And then finally, I'll summarize everything and hopefully inspire you about the future of the Scala programming language. Programming is hard, right? Programming is a very hard thing to do. And actually, I think that there's three major types of pain that can be alleviated by a statically typed programming language. And one of these has to do with imprecision. So imprecision is a pain where we're not able to precisely describe entities in business domains. Now, if we were dynamically typed programmers, we wouldn't really care about that. But because all of us here who came to this conference were believers in static type systems, or at least we like them, we enjoy them, we want to be able to model things very precisely. And when our programming languages fail to give us the tools necessary to do that, it causes us lots of pain. And it causes bugs. And it also leaks implementation, or it leaks information on business requirements, basically knowledge of the business requirements. If we're not able to encode that in the models that we build using our programming language, then that knowledge just disappears, or maybe it's embedded in comments, or maybe it can be reverse engineered from tests. But inevitably, if you're not able to create precise models of domain entities inside your business application, then you will be suffering either in increased development time or increased number of tests or in runtime errors. And one of the things that programming languages can do is give us tools to be precise. The second type of pain is a pain we're all too familiar with. In fact, I would say we, the statically typed programmers, are way more familiar with this pain than the dynamically typed programmers ever will be. Boilerplate, by and large, all the stuff that it feels like there should be a better way. There should be a better way for us to write this code, but we can't figure it out. We just have to duplicate here and duplicate here and duplicate here, copy paste here. All of these pains are actually very closely connected to the fact that we work with statically typed programming languages, which make it much harder to factor out certain types of boilerplate. As a result, we end up having to write a lot more code. Now, a lot of us have personally found that boilerplate, as long as it's statically type checked, is an acceptable trade-off for long-lived, large-scale code bases, because we would rather have the help of the compiler to ensure that what we're doing is sensible than eliminate all boilerplate and make everyone use Lisp. I mean, a lot of us would choose that, right? We're here at a functional Scala conference, so obviously we have a preference for static types. But that said, there can be a better way. And new programming languages, new versions of major programming languages can give us new tools in the quest for dealing with boilerplate. And then finally, I want to talk about something very interesting that's happening. Actually, it's been happening for a while, but you can see it a lot in the Scala community. And that is the fact that many times we are programming not directly inside the Scala programming language or whatever other programming language we're using. We're programming actually inside a programming language, or maybe not programming, but inside some sort of language that is itself embedded into our programming language. And this presents its own sorts of pain in a statically typed context. And new programming languages, next generation programming languages, they are in a unique position to help give us tools to deal with some of these pains. The first pain I want to talk about is one I'm very passionate about, and that's record overload. What is record overload? Well, in order to understand that, you kind of have to understand what a record is. What is a record? Well, a record is called a product type in functional programming, and it represents a sort of type level composition of other types. So in this example, I have person, which is a product composition of the type of first name, string, the type of last name, string, the type of age, int, and the type of gender, which who knows, maybe is string. So we have a four-way product composition. Products are very much records. They're very much like tables in relational databases, where we have different columns, and the different columns have labels. We call those the names of the columns, or we call them fields of a record, and they have types. Records are everywhere. Okay, so records are everywhere. You can see them everywhere you look. They're pervasive. So if we have an entity like user profile in our business, then we need to model that using a record. Because what does a user profile have? Well, it has things like age and country of origin and interests and location and all these other different things that we might want to stick in a user profile. That's a record. It's a table in a database, and it has a bunch of columns, all with a different type. It's a product type. And not just user profile, but like address. So if we want to model an address, we actually need a record. Why? Because product types allow us to say that an address is composed of multiple components. It's composed of the street number and the street name and the country and the postal code and so forth. And so we want our records to have all those things. So hence we must have a product type there to model that in a precise fashion. Credit card too. So credit cards, if you're building an e-commerce application, they actually have a credit card number, and they have a security code, and they have an expiration date. They have all these different things together inside a single record. So we need that record type in order to, that product type in order to precisely model that. Also a product, if you're building a product catalog, then every product has a price and has a name and it has a description and has a weight and it has all these different bits of information that we compose together horizontally using product composition. So we need a record to model that. Or an order, for example. An order consists of a whole bunch of different order items, and every order item is associated with a product and it has a price and so forth. At destination, maybe shipping address, that is a product. We need a product, a record, in order to handle that. But if we keep looking, we don't have to look too hard to find business entities out there that actually aren't records at all. An example of that is payment method. Payment method. Well, a payment method doesn't have to be a credit card. It could also be something like a wire transfer. And actually, if you think about it carefully, a wire transfer and a credit card, they actually don't share any information. So if we're paying with a credit card, then we need to supply the credit card number, which has a specific structure, an expiration date, a security code, and then the name on the credit card. But if we're paying with a wire transfer, we probably need totally different information, like a SWIFT code or an IBAN number or account number, recipient name on the bank. We need totally different information in order to pay via these two methods. Now, for a credit card, that's modeled very nicely by a record. In a wire transfer, that's modeled very nicely with a record. But a payment method could be either a credit card or a wire transfer. A payment method does not combine them both. So there's a saying here in America that when all you have is a hammer, everything looks like a nail. And in fact, if all you have is records, then you see records everywhere. That's all you see is records. And so you keep pounding the screws in with your hammer because you've never seen a screwdriver. Everything looks like a nail to you. And in fact, this is exactly what we do in many programming languages. So in the case of payment method, we build a record. Why not? We build a record. And our record will have getters that allow us to access bank account number and credit card number and Swift code and lots of other things. And in some cases, those will be null. Those will be null. And in fact, there'll be patterns of null because some fields won't make sense with other fields. So there will be certain patterns in how we do that. And it's not just Java and other programming languages that are guilty of seeing everything as a nail. Go, a programming language that I love to talk about, or maybe don't like to talk about. Go is a programming language that everything is a record to Go. And so when you return a value from a function, and this function may either succeed or fail, then the common way to handle this is to return two things. You return both an error and a success. So that's how you handled it in Go. Every function returns both an error and a success. And then by convention, if the error is nil, that means there's a success value. If there's a success value is nil, then that means there's an error value. What is going on here? This doesn't make sense. This is not a precise way to model this problem, but that's because the Go language, it has no precise way to model this problem. In fact, the inventor of Go programming language probably did not know that a way like this actually existed because records are everywhere. That's all we see. That's all we were taught. I was programming for 15 years before I learned there was anything other than a record. Before that, it was just records everywhere. That's the way we were all taught. That's the way we were all raised. It doesn't even stop with payment method, right? If you think more, you can find things like shipping method or an event. An event could be like a click on a web page and a purchase of a product. Those are two quite different events. Yes, they're both events, but also they store very different details, totally different details. I mean, maybe there'd be a timestamp in common, but other than that, they probably don't have anything else in common. They're totally different records. So there's no way to talk about that in the framework of records. And this problem I call record overload. Permission type is another example. So on to the next pane. And the next pane that you're probably all too familiar with is the pane of nulls. And you probably know that Tony Hoare, who is credited with inventing nulls, has often called them the billion-dollar mistake. But I'd like to suggest two things to you. First off, it's not $1 billion. It's at least $1 trillion mistake. And second off, this is an interesting way to look at this problem. Nulls exist precisely because all we had were records. And records just don't work to model the presence or absence of something. If we want to say that a value can either be there or cannot be there, well, how are we going to do that with a record? I mean, unless we're going to go the Go route, and we don't want to do that. So actually, programming language designers such as Tony Hoare and Algol, he invented this concept of a null, so we could have something that wasn't a record. So we could say this value is here or it's not. So nulls exist precisely because of record overload, pretty much. Why are nulls a problem? Well, for one reason, we look at a type like this in a statically typed programming language, and we say, oh, this contact variable, it has to be a contact, right? That's useful information, but we're wrong because it could be a contact, but it could also be null. The presence of null in an application infects all your type signatures with a lie. It's a lie because the type says one thing, this is a string, but the reality is it could be a string or it could be null. And this is so pervasive, so infectious, it contaminates every aspect of our application. In fact, if you look at a line of code like this, a simple one-line expression and storing it into a variable contact, you can see that there are three possible return values which could be null. The first one could be null, the second one could be null, or the last one could be null, or maybe multiple ones. You know, it could be two nulls, or I guess only one null because you can't dig into that. But the point is there's a lot of null going on here and across your entire program. And this could lead you to structure your program. If you wanted to carefully guard against these nulls, you would structure your program with a series of if then else statements. However, writing code like this is not fun. It is the opposite of fun. And it's a lot of boilerplate, a lot of boilerplate. And as a result, we don't do it. And what happens? Well, that happens, the null pointer exception. The null pointer exception that's confused programmers for decades now, invades our applications, brings our servers down, and ends up in the log countless times as we seek to track down and identify these null pointer exceptions that resulted from someone not handling one of these extra values that was appended into the type, one of these lies that are embedded in an otherwise statically typed programming language. Another very interesting pane, this pane here, is actually a boilerplate pane. And what it is we have some bit of our application. And that bit of our application, I always tell people every bit of our application needs to do three things in general. First off, it needs the ability to succeed in producing some sort of value as a result of the computation. It also generally needs the ability to fail. And we need the ability to fail because things can go wrong, and we have to account for that in our applications. But also, importantly, almost every part of our application, it needs context. Our application logic does not live alone. In fact, it might need a user repository if it's dealing with user entities. It might need a document service if it's saving user documents and restoring them. It might need some sort of application configuration if it's knowing where to look for secret keys that are necessary to interact with an API. It might need a cache if it needs to store things in a local cache or a Redis cache in order to improve performance. Might need an email service if it also has to trigger user emails based on activity. It needs all of these different things. And so what's the way to solve that? Well, in theory, we can always get dependencies to any point of our application by adding parameters to methods. In theory. However, I happen to know for a fact that there's almost nothing programmers detest more than passing parameters to functions, especially more parameters. That's one of the most detestable things in all of programmingdom is adding more parameters. It's boilerplate, it's work. Why should we have to thread all of these dependencies throughout our entire application? And in fact, a lot of people have said, well, you shouldn't have to do that. And that has given rise to frameworks such as Juice and Dagger and Spring DI. And in Scala, we have our own dozen or so different solutions for so-called dependency injection, all of them which are aimed at alleviating the pain. Actually, there's two reasons these frameworks exist, both to simplify wiring, but also to eliminate the pain of threading dependency information context into our applications. This next pane that I'm going to talk about, I call leaked abstraction. But before I can describe exactly what that is, I have to talk about what abstraction is. And generally, I think you can consider abstraction to be the act of capturing the ways in which different types are all similar in some well-defined way for the purposes of writing generic code that can support all of these different types, regardless of the ways in which they're different. It's like a lens that we apply and we look at a bunch of different things, and now through this lens, we see only the ways that they're similar. And we don't see the ways that they're different because we want to treat them as being the same from the perspective of writing some generic code, so that generic code can therefore be utilized across all of these different data types. That's the idea, for example, behind generics in Java and in Scala, is we have generic lists and generic vectors and generic maps. They don't care about the differences between different key types and value types and element types. They ignore that. And they do that because we don't want to have, like Go, we don't want to have lots of different structures specialized for every element type. We want our structures to not know about those differences and only see the ways in which these things are similar. So leaked abstraction occurs in almost every scenario where you're trying to use your programming language's means of abstraction in order to create generic code. An example would be, let's say we have an endpoint in our system that returns values of type person. So this endpoint will be deployed maybe to gRPC or maybe to a REST API or maybe GraphQL, who knows, but we're going to deploy this endpoint. And we have some sort of function like publish here, which takes that endpoint and publishes it. Now, let's say after looking at this for a while, we decide we need to publish a different endpoint. And after inspecting the implementation of publish, we see, oh, it actually doesn't really depend on the structure of the endpoint that is returned by the endpoint. So this publish method can, in theory, work with endpoints that produce person objects, but it can also work with endpoints that produce user profile objects, and it can also work with endpoints that produce shopping history information and so forth. So we want to make this publish method generic. We want it to forget its knowledge about the person structure and only look for the ways in which different types, like the user profile and the person object and the shopping history and so forth, are similar. Then how would we do that? Well, the way you're going to read about in any sort of textbook object-oriented book is introduce an interface called endpoint A. And this endpoint A, that generic type parameter, can describe the type of value that is produced by the endpoint. And then you can recapture the original specific solution by creating a class that extends that and specializes that type parameter A to be person. So now we have a person endpoint. This allows us to talk about the ways in which lots of different endpoints are all similar. Then we have to modify the publish method so that it takes a generic endpoint. However, we have a problem. Taking an endpoint of A for any type A is not sufficient, because ultimately, when we publish this endpoint, the endpoint itself, or the publishing logic, it needs to be able to take that A value, whatever the endpoint returns, and it needs to be able to convert it into JSON, or maybe into some other format, but let's just say it's JSON in this example. How is it going to do that? The problem with this publish is that it's forgotten everything about the concrete type. It now has no structure to deal with. We have to reintroduce structure. And how we can do that is through this sort of ad hoc polymorphism here. We introduce an interface called JSON serializable. And this interface allows us to convert an object into JSON by calling the serialize method on that object. And what we do is we extend this interface in our person class. And so now our person class is obligated, actually the compiler will make us implement the serialize method and return that JSON value here. So with this change, we can go back to the publish method and we can change it. And we can say, hey, we can publish any A that actually is a subtype of JSON serializable. So as long as it extends JSON serializable, we can publish it. Problem solved, right? Well, not all that well, actually. It turns out there are some serious drawbacks to this very common form of object-oriented abstraction. And the two most common drawbacks, the first common drawback is the fact that this works okay for serialization. However, it works horribly for deserialization. Because we take this interface and we extend it by our domain object, person in this case, we have a natural way to take one of those objects and serialize it merely by calling serialize. But how about if we have to deserialize one of these person objects from JSON? How is that going to work? Well, we would have to call it on an existing JSON object. So that forces us to make our domain model mutable, first off, because we have to be able to create some sort of dummy value and change those values after you call deserialize on the dummy value. But then beyond forcing us to make our domain object mutable and all the complications that arise from that, it actually forces us to have and pass around these dummy values, or maybe to use reflection to instantiate them, which is common in Java with externalizable and other things like that, which is not a great solution to this problem. In addition, we have another much more serious problem, that object-oriented abstraction is anti-modular. What I mean by that is there could be lots of different data types out there that we didn't make. We don't have control over their inheritance hierarchy, so we cannot make them extend JSON serializable, which means we can't actually have an endpoint that returns any third-party data type because we would not be able to call our publish method. As a result, object-oriented abstraction, it's actually, in my opinion, a sort of failed form of abstraction this does not work well. It's actually a leaky form of abstraction because it has all these edge cases and corner cases that don't fit well. And this is an artifact of the programming languages that we're using, which encourage us to abstract using subtyping. The next problem I want to talk about is also a boilerplate problem. And this problem arises when we use object-oriented structures in order to model data. An example would be this person data type. So in Java, if we had a person data type, we might model it like this, as having a string name and an int age, so having these two fields. And this would be our model of record. This would be a record that models people. And there's lots of boilerplate that I'm not showing you. In Java, we would probably have getters and we would have setters and we have lots of other things. But the main type of boilerplate I want you to focus on here is the equals and hash code method, which have to be written either by hand or by your IDE or potentially by some tool like Lombok, which is going to use annotations to generate code on the fly and compile it as part of your build process or startup or whatever. Why do we have this problem? And we have this problem because the data that the means by which languages give us to create data models are grossly underpowered. I mean, think about this. This is 2020. 2020, computers have existed for decades at this point, and we are having to tell our computer how to compare two pieces of data to see if they're equal, or how to compute a hash code from one. We're having to tell our computer that very, very explicitly. And I know what you're thinking. Hey, we're in Scala. We have it easy. We live a life of luxury because every time we want to create a record, all we have to do is case class it. And once we do case class, then we get a free equals and a free hash code and a free copy method and free constructor in the companion object. We get all that stuff for free, which is great. I don't want to underestimate the value that brings us as a developer, but also I want to emphasize the fact that the applications that we create in this day and age, they're microservices, they are GraphQL APIs, they are REST APIs, they are data processing and analytics APIs, machine learning workflows. They are data-intensive applications. Our world revolves around data to a massive degree. And every ounce of boilerplate that we have to create to add functionality to our data model is an enormous wasted effort. And I think that that's partially because the people inventing programming languages are not necessarily the ones forced to have writing all this data transformation and processing code. They haven't necessarily lived with the pain of all of this. And then the tools that object-oriented programming have given us are versatile. You can use a class to model a service, or you can use it to model a data. And with that versatility comes a loss of specificity. And that's what we're missing, is extraordinarily powerful data that is specific, that is focused on being data and data alone, and not even able to be used to model anything like a service. And even though we have it better in Scala, we actually don't have it very good at all. Because what happens if we want to order person objects? Okay, so good luck writing that one. You're going to have to write some code if you want to compare two person objects to see which one comes first. Or what happens if we want to encode it in JSON? Well, write that, or, code gen it. Or how about encode JSON? Or how about debug it? Print out a tree, do diffs, do all sorts of interesting things that you can with true data that you can't do with services. Good luck getting that out of it. Or how about migrating it from one version of a case class to another? Can't do that. Or how about table? Some sort of flat tabular representation of the information content of this case class. No, you can't do that. You can't do any of these things. And that's because even in Scala, even though Scala is better, the data models or the tools that were given to construct data models are grossly underpowered, and they're not adapted for this world in which the vast majority of programming is munging data, some form of data munging. So obviously there are solutions to these problems, and one of them, Go's solution, is a code generator. When your language fails you, you turn to code generation. You start printing programs. When your programming language lacks the means of factoring out certain types of boilerplate and duplication, your only solution is to print line a bunch of code that you don't want to write by hand. And this is particularly, it's prevalent in almost all statically typed programming languages. We have code generators in Scala as well, although they're not well used. It's extremely prevalent in Go, where, for example, this project has nearly 2,000 stars and 27 watchers. I don't know if you know much about GitHub, but this is a hopping project here. This has got some traction here. This is a code generator, and it's quite successful. That's what happens when your programming language fails you. And then the last pain I want to look at tonight is the pain of dynamic DSLs. So I find it highly fascinating that actually a lot of programmers spend the majority of their time, maybe more than 50%, a lot of Scala programmers spend the majority of their time working not directly in Scala, but working in some other language that is embedded inside Scala. And maybe you know that, maybe you don't know it. But for example, if you're using Spark, you are actually working in an analytics and data processing language that has itself been embedded into the Scala programming language. And of course, it's not just Spark. There's many other examples of working in what I call dynamic DSLs. The reason why I call them dynamic DSLs and why they're a pain point is because when you work inside a language that is embedded into a larger host language, then even if the host language is statically typed, then the DSL, the little mini language that you're using inside that language, is not necessarily statically typed at all. And in fact, it is very difficult to make a DSL that is statically typed. Generally, even though the program that you write will be statically checked by the compiler, you will be able to form other programs, if you will, inside this mini language that you're using embedded inside the host language, which can go wrong at runtime. In other words, you're using static typing in the large, but you're using it to build a model which is itself dynamically typed. And as a result, the host programming language, it's not able to check and make sure that you're doing sensible things. It's almost like you're paying for the cost of using a statically typed programming language without all the benefits that come with using a statically typed programming language. Other examples of this pain include SQL. So I have seen so many Scala code bases where you query these relational databases by writing gigantic strings and then inserting values in the strings and so forth, and looping over result sets and so forth. And ultimately, this is an example of programming in an untyped language inside a typed language. And all that SQL code you're writing, you are not benefiting from any of Scala's features. Even though your program might be statically typed, the queries that you're writing inside Scala, that mini language that's embedded inside the host language, that's dynamically typed. So at this point, if you are a Scala developer and you're writing tons of SQL and Spark jobs and other types of things, it may be that you're actually benefiting not very much from static typing. And there are reasons why this is the case, but fundamentally they all come back to the fact that it is very hard to make a mini language embedded inside a host language statically typed. And that's because of features that are possibly missing in programming languages, or even if they're not missing, they're very hard to use and use well. And another example, even though we don't unfortunately have this yet in Scala, is a really great way of treating infrastructure as code. It's called Pulumi, and it allows you to create sort of declarative description of your configuration as pure code. So it's like Puppet, but sort of beyond Puppet or Chef, sort of a next generation version of that take of infrastructure as code. And again, it's an example of creating a DSL. Now, in this case, it happens to be in Python, but that's not a bad take, actually. If you were doing this in Scala and your little domain language was similarly going to be a dynamic domain language rather than a statically typed one, honestly, there's no real drawback to doing it in Python versus Scala if you're not going to be able to take advantage of the host language ability to do static typing. So, in the face of all these pains, which span the categories of boilerplate and dynamically typed DSLs and imprecision, what does Scala 3 potentially bring to the table? Well, I'm very excited about Scala 3. It's been in development for, I think, more than 10 years now. And there was never any guarantee we would see this language. We're seeing it because of sort of a combination of factors, one of which is that Odersky and crew made the decision to take what was an academic research project called Dotty, which gave Scala a much more sound theoretical basis. And it was decided that would become the next version of the Scala programming language. That's why that I'm sitting here today in this chair at Functional Scala 2020 giving a talk about Scala 3. It's because combination of different factors all combined to give us what is essentially a product of sort of next generation research from academia. This is Scala 3, but it's not purely an academic project. It's been informed by Scala's long history in the commercial sector. So we've been using Scala for 20 years now. We know a thing or two about writing Scala. And one of the things that I like about Scala 3 is that it learns from that rich history. Scala 3 does two things. Number one, it cleans up on many of the problems with Scala 2.x. So many of the beginner gotchas and all sorts of things that people ran into in Scala 2.x, those are cleaned up in Scala 2. And not just sort of syntactical things, but also semantical things, also type theory things. So Scala 3 is powered by the dot calculus, which is sound, and many constructs which were not sound, they may have been cool, but they were not sound. In Scala 2.x, they've been removed out. So Scala 3 has rock solid foundations, and it's learning from its long history of production usage. Number two, Scala 3 is cutting edge, and I mean that in a good way. I mean that it is taking sort of very fresh results from academia, and it is applying them to a commercial grade functional programming language. It's giving us features that are simply not available anywhere else in any other mainstream programming language. I hope you attended Adam Orsky's talk and Alexander's talk and all these talks that talk about some of the capabilities coming to Scala 3, because that will give you an appreciation for the fact that the powers that are coming to a language that is as mainstream as Scala is, and Scala is actually relatively mainstream compared to Haskell and Agda, Coq, all these other more esoteric programming languages. Scala is very mainstream. We are getting stuff that has never, ever, ever been done in any language that is as mainstream as Scala. And you are going to be able to put this stuff into production. These are game changers. You should be excited. After attending this conference, you should be excited about Scala 3. Scala 3 is here to help. And it's going to do that by introducing a series of features that will eliminate or reduce many of the pain points that programmers deal with in every single day in their commercial programming or code bases. And not just programmers in Java, but also programmers who work in Scala. So many of the pain points that are addressed by Scala 3 were not addressed either at all or not fully by Scala 2. So this is a huge upgrade. If you're already using Scala, if you're already sold on Scala, then trust me, Scala 3 has a lot of things to make your life easier and better, to allow you to be more precise about the way you model data, to allow you to cut down on the amount of boilerplate, and to allow you to work much more safely with statically typed DSLs. And one of the ones that I'm very excited about is enums. So remember, record overload, that pain that's coming from the fact that so many programming languages see everything as a nail to be hammered by the record hammer. Well, Scala 3 definitively eliminates that by introducing first-class support for algebraic data types in the form of enum. So Scala already had case classes, which are product types. It had a way that you could emulate some types, and actually it was pretty good, but you have to acknowledge that CL trait is an emulation of a sum type. It is not exactly a sum type, and an enum is exactly a sum type, even down to the fact that when you construct a term of an enum, you get back the type of the enum and not a more specific type. So that's very important for type inference. Anyway, this enum construct, just like case classes allow you to model products that have this component and this component and this component, enums allow you to model sums, which are going to be constructed either using these details or these details or these other details. So to model a payment method using Scala 3's enums is trivial. You just say enum payment method and you have case wire transfer, case credit card, done. 100% type safe, extremely precise method that involves zero boilerplate, and you don't have to know anything about the sort of peculiar way that you had to model this using Scala 2.x constructs, including sealed traits and storing the constructors in the companion object and making sure to extend the sealed trait from all of those constructors and so forth. All those irrelevant mechanical details are gone. And now replacing them is a high-level construct that models intention. That is the overriding message of Scala 3 is let's focus on intent and let's get rid of mechanics. And enums allow us to exactly do that. And look at that. I mean, how can you look at that and not think that that's beautiful? So that is beautiful. That is every bit as good as sum type in Haskell. And actually, it's a bit better because if you want to hold on to the type of one of those terms, you can do that. And in Haskell, those don't define their own types. So if you want to package up all that information, you have to use a tuple, which is not as pleasant to deal with either in Haskell or in Scala. So this is a sum type, like a FP first class sum type, done even arguably a bit better than how they do it in Haskell. And then modeling things like event, it becomes trivial. And enums are quite well thought out. I'm very impressed by the attention to detail. They work great with polymorphism, so generics, as well as contravariants and covariant annotations. Another pain that we talked about, which arose, in fact, from the lack of anything other than records. So what other programming languages were missing was this concept of a sum type or an enum. Enums in Scala 3, by the way, are way more powerful than enums in Java. Enums in Java can only be utilized when you have a fixed small number of values. For example, day of week, there's 7 of them, so you can use the Java enum, whereas the Scala enums can be utilized for infinite values because the only thing that has to be finite is the number of ways to construct them, and to deconstruct them, we need to pattern match. So Scala 3 enums should not be confused with Java 2 enums, or sorry, Java enums. Scala 3 enums are way more powerful than anything that exists inside Java or is likely to exist. And then on top of that, sort of, Scala 3 is adding support for explicit nulls. And this probably would have been controversial if Scala had decided to do it 15 years ago. But this day and age, I think null is widely regarded as a mistake. So new languages like Kotlin, they tend to have support for explicit nulls baked in, and now Scala 3 is giving us that very feature. And the interesting thing about Scala's support for explicit nulls is it's actually baked on much more general purpose features. So some programming languages have special case nulls. Scala doesn't do that. Scala just gives us very powerful language constructs that allow us to eliminate the pain of nulls. And how we do that in Scala 3 is we actually use union types. So when you turn on that feature of explicit nulls, any nullable type will now be string or null. For example, a nullable string will be string or null. And this feature by itself, it would be somewhat interesting, but where it gets really interesting and where it has the potential to totally eliminate all cases of null pointer exceptions is the fact that Scala 3 has a type of flow sensitive typing, whereby Scala can look at what you're doing inside if statements, and it can utilize that information to add typing information to its type checking phase. An example would be if we have something that's string or null, and we check to see if it's not null, then in that code branch, Scala adds a bit of more type information and says, hey, this type here is definitely not null, which means that it's a string. And so we can safely, inside that code block, we can safely use that value as if it were a string, because Scala knows it must be a string, it cannot be null. So the combination of union types and flow typing mean that the days of null pointer exception are over. So even if you use null in your Scala programs or interop or stuff like that, you can say goodbye to nulls. And of course, you can use these same language features for doing many more things than just eliminating null pointer exceptions from your application. In addition, Scala is gaining an interesting new feature called context functions. And context functions have been used to explore effect systems and a variety of other things in the Scala 3 programming language. But one of the things I think that deserves a serious look is to what extent context functions can make it easier to get dependencies to our applications. So in an ideal world, Scala would be able to infer what we need, and it would be able to thread that automatically. And to do that, we need a form of context propagation together with support for intersection types. And Scala 3 is bringing both of those to the table. So it remains to be seen if a context function necessarily is the solution to this problem. But I will say there's a lot of interesting and powerful so-called contextual abstractions in Scala 3, and that between context functions and also the improvements that have been coming with respect to contravariance and intersection typing, I would be surprised if we don't end up with a better solution for the context propagation problem, making it easier for you to get things to parts of your application that needs them without having to resort to anything that's type unsafe or driven by XML files or that requires lots of manual boilerplate. And of course, one of the things I'm excited about is the fact that Scala's improved support for contravariant type parameters together with its support for intersection types is going to make solutions like Zio, which already have baked in support for context propagation, it's going to make them much more powerful and much more able to infer correctly in a variety of situations. So how about this problem of leaky abstraction? This problem that it's not easy to use the object-oriented way of abstracting over different data types in order to solve problems in creating generic code. Well, Scala 3 has a very, very powerful solution to that problem, and that solution is called type classes. What type classes allow us to do is to take that interface that we would ordinarily mix into an object like person and pull it out and make it stand alone. And it's possible to do that in Java, honestly, and it even is done in Java a bit, but it's so painful to program in that fashion without explicit language support that most people don't do it. You have to have a very high boilerplate tolerance. If you want to solve the leaky abstraction problem, you can do it, but only with a boilerplate problem. So it's pick your poison. That's many times what programming languages force us to do, is pick our poison. So even though you can do this technique in Java, it's not done. But what you do is you just take that interface, you pull it out of the object, and you make it stand alone. And that solves two problems. First off, it solves the problem of being able to model things like deserialize, which actually construct values of a given type. So deserialize takes JSON and builds you that person. And you can solve that directly because you can have a reference to, in this case, a JSON codec. You can have a reference to that codec that's outside of any person object. It just lives standalone. It's independent of it. In addition, it solves the other problem of third-party data types, as we'll see in a second. So utilizing these type classes is beautiful. It's amazing. It's compact. And Scala 3 has well thought out this issue. Basically, all the drawbacks that were keeping people from utilizing type classes in Scala 2 have been dealt with. And as a result, even though type classes have enjoyed some level of success in Scala 2, they never achieved mainstream adoption. And by mainstream, I mean you can see them in everyone's code base. You can't see type classes in everyone's code base. You have to look in. It's a little bit bigger than just the functional Scala subcommunity. It's bigger than that, but it's nowhere near mainstream in Scala 2.x. And by giving first-class treatment to this concept, I think what Scala 3 will succeed in doing is making type classes pervasive, giving this power to everyone. And that's what happens when you move from the language of mechanics. So Scala 2 didn't give you type classes, it just gave you low-level features that you could cobble together in some esoteric fashion to emulate the features provided by type classes. Scala 3 is giving you the finished product, and it's built to solve that exact problem. It solves it very well, and it's fairly easy to teach and fairly obvious how to use it once you've been taught how to use it. And how you, instead of using type bound in order to solve a problem like our publish function here, we just use something called a context bound, or we use a using statement. They're totally equivalent. We just say we want to use some features that this type needs to support. For example, we want to use a JSON codec for this type. And all the pains of the old style encoding go away. And then we can take and we can build these things, not just for our own data type, but for third-party data types using a given construct. And given just provides an instance of this functionality to the Scala compiler, so the Scala compiler can use it when it's looking for that capability across that data type. So very powerful, very straightforward to teach, very relatively easy to use. And then it should probably be no surprise after seeing some of the talks at Functional Scala that one of the most interesting areas of Scala 3 is metaprogramming. So metaprogramming is basically the ability to generate code at compile time in a type-safe way. I don't mean printing lines of text to a file and then compiling that. That's not really considered metaprogramming. That's what you do when you don't have metaprogramming. Metaprogramming, you have a structured representation of code, and you have the ability to generate this at compile time and to use that structured generation of code as you further in the compilation process as you're generating bytecode. Metaprogramming is enormously powerful, and it's going to open up the doors to all sorts of things. And in fact, it is boilerplate's kryptonite. So metaprogramming is the key to eliminating, or at least greatly reducing, all of the boilerplate problems that arise specifically because we choose to work in a statically typed programming language. So this is our superpower here that enables us to have our cake and eat it too. Ordinarily, we get to choose between boilerplate together with static types, or no boilerplate and everything dynamic types. And metaprogramming, especially in the Scala 3 variant, which is very, very good, says no, you get to pick static types and you get to pick no boilerplate. Congratulations, you can pick both of those. And there is no other mainstream programming language that allows you to pick both of those. It doesn't exist. Scala 3 is first in class, being the first mainstream programming language to allow you to pick both of those at the same time. You've seen example from Alexander on what this could do for querying relational database systems. Imagine being able to essentially write code that works sort of at compile time, generating at compile time SQL queries, but also works in your code base to do similar things. This is a capability that's a sort of staged metaprogramming has the ability to do, and it's enormously powerful. But I would say that one of the more immediately obvious applications of metaprogramming is going to be powering a feature called type class derivation. And type class derivation is how we overcome the problem of underpowered data. So remember our case class, our friendly little case classes that have equals and hash code, which is great, and copy, but they have nothing else. Imagine if they had lots of other things. Imagine if we had rich, extraordinarily rich functionality on all of the hundreds of different data classes that we create in any given domain. Well, with type class derivation, you don't have to imagine anymore. That's coming, and it's going to come really fast in a first-class way. Scala 2 developers, we've been able to hack some of this with macros to varying degrees in a sort of unsupported and ad hoc way that has exceptions and edge cases, and everyone's afraid to write them. Very few people know how. It's a bit of a dark art. They're not documented. That's not the same. With Scala 3 metaprogramming, we are going to have the ability to add these rich features to our data types in a way that's robust, that's principled, that doesn't have edge cases, that's well documented, that's very well maintained, and that's going to attract a tremendously large audience compared to the audience for Scala 2 macros, which is very tiny. There's 20 people in the world who write those things. Whereas with Scala 3, even though this is not something everyone in your team is going to be able to do, probably there's going to be multiple people who are more than comfortable writing Scala 3 style macros to benefit from some of these metaprogramming capabilities. And type class derivation, it gives you a very powerful way to leverage metaprogramming to enrich data types constructed from case classes and enums. That's exactly what you're going to do. So in Scala 3, Let's say we want to take our person, which comes from, or which comes with free equals and hash code, and we want to enrich it. What do? Well, we type derives followed by ordering. Done. I love it. Just add debug, add encode JSON, add decode JSON, add a tabular data representation, add anything you want to that. That's how easy it is to get functionality for free for all of your case classes and enums. It doesn't matter, you have hundreds, thousands of different data types. You want rich, powerful functionality on all of them for free just by typing a few characters? Yes, please sign me up for that. The amount of code that this is going to eliminate in modern applications is tremendous. And the fact that this is going to be so open and well maintained, and anyone can come along and add these things, which is enormously powerful. You know, for a while, Haskell had these things, but they were rigidly baked into the compiler. The compiler had to know specifically how to do them. And of course, they generalized that after a while, and now a larger class of people can write them. But we're getting the sort of broader generalization of this feature right out of the box in Scala 3. And it's going to revolutionize how you work with data-driven applications, giving you all of this rich functionality for free. And that's just a peek at the future of metaprogramming. This is a shiny box with some green glowing mist inside it. And we don't know exactly everything that's in there because we haven't had time to explore. But I think if you've been hanging around the chat room, the spatial chat for the past few days, you've gotten the sense that there might be a lot inside this box. We're just beginning to discover some of the powers that this will give us, the powers to eliminate boilerplate, and in particular to make our DSLs that we're working with statically type safe. So not just sort of SQL, which you've seen with Quill, but also potentially machine learning and analytics and infrastructure as code and all sorts of really interesting things that can potentially staged computation, writing code in Scala that is deployed to GPUs and also clusters of CPUs and also to assembly. The ability of Scala to do compile time code generation through metaprogramming is extremely powerful and is going to have applications that we're only just beginning to get a glimpse of. Spark changed the world. I mean, that should not be a surprise to you. Spark changed the whole world, not just the Scala community. Obviously, Spark was very important to Scala's success, but that one DSL, which is still somewhat dynamically typed, it's a little statically typed, but it's also a little dynamically typed, it changed the entire world. Now, imagine what could be built on top of all of the rich functionality and features of Scala 3. And not just in the domain of data processing and analytics, but all the other big nasty domains out there that are waiting for a killer solution like Spark to come along and change the world. It gets me very excited to think about that. So I hope I've given you both some tools that you can take back to your company. You can say, hey, these are the pains that we're dealing with all the time. We deal with imprecision. We deal with boilerplate. We deal with the pain of working with dynamically typed DSLs. And hopefully you can take that and you can take it back to your work and you can say, Scala 3 is here for a reason. Actually, it's here for very good reasons. Scala 3 is here to change the way that we write software. It's here to give us precision in the way we talk about data models through features like enum, as well as union types and flow typing, which are powering explicit nulls and other features that I didn't have the time to talk about. It's here to give us the ability to express ourselves with economy, concision. We would like to not copy paste our code into lots of different files and search and replace changes. We would like not to have to use Jennifer to generate massive piles of Go because our programming language has failed to give us the ability to eliminate boilerplate. And we would still like to have the power of static types as well, because they give us the help of the compiler to make sure that our code is doing what it should be doing before we even go to run it. And then finally, we would like the ability to create statically typed DSLs that have, like Spark, sort of world-changing power, but that are safe to work with. We can work with them in Scala, and we can know that the programs we form in the language that is embedded into Scala won't go wrong in some very meaningful sense. And all of this, boilerplated precision and statically typed DSLs, Scala 3 has the features to totally revolutionize how we are building applications. So your app on Scala 3, in my opinion, it's going to be awesome. It's going to be awesome. Now, that said, early days, be patient. There will be bugs, there will be setbacks, there will be tweaks that have to be made. There will probably be 11th hour changes. I think there actually are a few in the works, but that said, this is a very important time in the history of the Scala programming language. And if you are a Scala developer or you're considering being a Scala developer, then you should be very excited and be very proud to be a part of the future of this programming language. So I want to thank you for attending my talk. I will be taking questions later in the Evolution booth. And also, if you have enjoyed my teaching style or whatever, I do one-on-one mentoring on the Patreon there. You can check out that link. And then the next event you can catch me at, and not just me at, but also a number of other Zio contributors at, will be Zio World, which we have not yet announced. We'll announce that probably in early January, but this will be a very exciting event where we talk about the future of Zio and all the amazing additions coming to the next version of Zio in the near future. So be sure to check that out. All right, thank you very much.